Yeah, so let us go back to where we stopped the last time, which was the logistic map, and we discussed the idea of a generalized dimension. And to recall to you, the generalized dimension dq was defined as the limit as epsilon goes to 0 of 1 over 1 minus q, the log of 1 to n of epsilon mu j to the power q divided by log 1 over epsilon. This in the case if you took the full phase space whose measure is unity, normalized to unity, and you broke it up into cells of various kinds, and this is the Cj, the jth cell, and mu j is the invariant measure associated with this. So you begin to see that I have in mind a system which displays chaos, which is certainly ergodic and which displays chaos, and in which a typical phase trajectory wanders round and round in the phase space or some portion of the phase space like an attractor, and I take that portion, I break it up into cells Cj, and I associate some letter of the alphabet with each of these cells, and I do the symbolic dynamics of the trajectory in the sense that I keep track of at each iteration in which cell the trajectory is to be found, a typical trajectory is to be found, and having done that, then I compute this generalized dimension here, which is some kind of weighted sum over this invariant measure of the jth cell raised to the power q, and this set of numbers dq gives me some information on the way the attractor is, on the nature of the attractor. In general there is no reason why these dq's should be integer numbers. Q need not be an integer by itself, and dq is some function of q, and the general statement I made was that dq is a non-increasing function of q. In other words, as q increases from minus infinity to plus infinity, dq decreases, maybe not monotonically, but certainly not non-increasing. So the statement, specific statement, was that if q prime is greater than q, then dq prime is less than equal to q. That was the statement I made about these generalized dimensions. The next thing we saw was that in the case of one dimensional maps in which the density was uniform, you could break it up into say n cells of equal size 1 over n, and then it was a easy matter to show that dq was equal to 1, the topological dimension of the attractor. The fractal dimension is the same as the topological dimension, the entire interval was the attractor. But if the invariant density or the measure is not uniform, then this is no longer true, and the question was, what is it in the case of some of the maps we have looked at for which we know what the invariant density is. So let me take that up now and show you what it is for the logistic map at fully developed chaos. So this is the next task, to compute dq for the logistic map. At mu equal to 4. So if you recall, the map function f of x is 4x times 1 minus x, and the invariant density, in this case the normalized invariant density, was 1 over pi times square root of x times 1 minus x. Okay. Now what do we do? Well, here is the interval 0 to 1. I break it up into n cells of equal size. So this is 1 over n, this is 2 over n, and so on, and this is cell C1, this is cell C2, and finally you have n minus 1 over n, and this is cell C sub n. And I am going to compute this measure for each of them, take the limit n goes to infinity, and compute what dq is. So that is our program. And what is mu j? For the jth cell is an integral over Cj but Cj runs from j minus 1 over n to j over n dx times rho of x. But what is that equal to? Well, this is pi times square root of 1 minus x times 1 minus x, and remember n is going to become very large and the size of each cell is going to become very small. So what does this become approximately equal to? It is approximately equal to, in this cell, in any of these cells, say the jth cell here, the value of that integral as this interval becomes smaller and smaller is the value of the integrand at the midpoint multiplied by the length of this interval, and the length of the interval is 1 over n, and the value of the integral at the midpoint is 1 over n pi 1 over the square root of j minus a half over n times 1 minus j minus a half over n, because the cell runs from j minus 1 over n to j over n and the midpoint is j minus half over n. So that is what mu j is, and therefore dq can now be written down at least formally, and we have dq equal to a limit n tending to infinity, because I put epsilon equal to 1 over n, 1 over 1 minus q, the log summation j equal to 1 to n, that mess 1 over n pi square root j minus half over n 1 minus j minus half over n, this whole thing raised to the power q divided by log n, 1 over epsilon is n. This is the quantity whose limit I want. Now this suggests very strongly, you have a sum from 1 to n, this suggests very strongly that you actually have an integral here. You could convert this sum back to an integral once again, and what would this integral be? Well, if I forget about this factor and then I put a 1 over n outside, this would be related to the following integral. It would be related to 1 over pi, apart from a factor pi, x times 1 minus x to the power q. It would be related to this integral. Do you agree? Because it is a Riemann sum, and I can always write this Riemann sum back as an integral provided the integral converges. And when is it going to converge? When is this integral going to converge? It has got singularities at 0 and 1 out here, and it is clear that it is going to converge because there is a square root here, q over 2 should be less than 1. If it is greater than 1, this diverges. When q over 2 is equal to 1, you have a dx over x that is logarithmically divergent. So the integral converges for q less than 2 and diverges for q greater than or equal to 2. So it immediately means that you have to consider two cases separately. You have to consider case 1 q less than 2 and case 2 q greater than or equal to 2 separately. For q less than 2, so let us look at that first. dq is equal to limit n tends to infinity 1 over 1 minus q log summation j equal to 1 to n. Let us get this n out of here, and that is n to the minus q, and then let me take it out of the integral. So log n to the minus q comes out of the integral, and then what I have here is 1 over pi square root of j minus half over n 1 minus j minus half over n to the power q, and it is really saying take the function x times 1 minus x and take the midpoints of those guys, the value at the midpoints, and consider this sum. Now if I divide that sum by a 1 over n, this quantity in the limit n tends to infinity is exactly equal to the integral from 0 to 1 divided by the whole thing divided by, so I divided by n, therefore I better put it back, so log n to the 1 minus q. So please remember, I divided by an n in order to convert this to an integral, and I have to put that n back there. Divided by, I get rid of this, and this is log n to the 1 minus q, because 1 minus q log n is log n to the 1 minus q. That becomes very, very simple to evaluate. So this quantity is equal to dq is equal to, well, the first term is clear, so log of this times that, and I take this out and it gives me just unity, it's very clear. So this 1 plus the limit as n tends to infinity of this sum divided by this. But you see, this sum in the limit is simply the integral from 0 to 1 dx over x times 1 minus x pi times square root of this to the power q. That is all it is, because that is how we got this to start with, divided by log n to the 1 minus q, and recall that q is less than 2. So what happens there? What happens to this thing here? So I put a 1 over 1 minus q outside, and I have a log n. This integral is finite, this integral is finite, and therefore when n tends to infinity, this log n in the denominator ensures that that term goes to 0 completely, because this integral is finite, it converges. So it is immediately clear this is equal to 1 for q less than 2. D0 had better be equal to 1, because that is exactly what the fractal dimensionality of the attractor was, and the attractor was the unit interval, the full interval. So D0 was in any case equal to 1. Now we discover that dq for all q less than 2 is equal to 1. If you had a uniform density like in the Bernoulli shift or in the tent map at fully developed chaos, then dq is equal to 1 for all q. But here for q less than 2 we can assert it is 1, but we have to re-examine the problem for q greater than 2. So let us now do the next step, and that is to go back and ask what happens if q is greater than 2. So we have to go back to this, and then we end up with, so this is the second part, q greater than or equal to 2, when we can't convert this summation into an integration, because the integral does not converge, but the sum is finite, completely finite. So what do we do in this case? This case dq equal to limit n tends to infinity, in the denominator of course you are going to get log n to the 1 minus q, so let us put that here, to the 1 minus q, but in the numerator you have an n to the q which comes out there, but then you can't convert the rest of it into an integral, so there is not much use doing that. On the other hand, let us simply multiply through by n, and this n goes away because you get an n squared with a square root that cancels this, and in the numerator if I give myself a little more space, this thing becomes limit n tends to infinity log summation j equal to 1 to n. Let us multiply through by n, so we have a 1 over pi times the square root of j minus a half n minus j plus a half, this whole bracket to the power q, and the n squared cancelled out with this n here, divided by log n to the 1 minus q. I have to deal with this. Now what sort of sum is this? It is clear that for small j, j near 1, near this end, the lower end, these terms, the denominator is going like 1 over n to the power q over 2. So those terms go to 0, the terms for small j. Now we are going to have j n very large, so the terms for small j are going to go to 0 like 1 over n to the q over 2, because this factor is going to dominate and these are finite small numbers. On the other hand, at the other end of the sum for j near n, this is going to be some small number and you are going to have an n here. So once again the terms are going to go like 1 over n to the q over 2. The terms in the middle near n over 2, for example, both these factors are going to be of order n, because this is going to be like n over 2, that is going to be like an n over 2, and therefore those terms are going to disappear like 1 over n to the q, because it is the square root of n squared. So the conclusion is you have an infinite sum, a very large number of terms for a very large n. The terms at the lower end are going to disappear like 1 over n to the q over 2. The terms at the upper end are also going to disappear like 1 over n to the q over 2, and the terms in the middle are going to disappear faster like 1 over n to the q itself. So this whole thing could be written in the following form. The whole thing could be written as equal to limit n tends to infinity. One can make this much more rigorous, but this is as simple a way of understanding it as any. Log of n to the power minus q over 2 summation j equal to 1 to n times something or the other which will give you in the limit a finite sum, because this is the rate at which every term vanishes and the ones in the middle are going to go to 0 even faster, but certainly there are lots of terms of this kind, contributions of this kind, divided by log n to the 1 minus q, where this sum tends to a finite, not infinite, a finite non-negative quantity, finite limit as n tends to infinity. Having pulled out the dominant n, this is what the rest of it is, and that immediately implies that this implies dq is equal to, since in this case there is an n in the denominator that cancels against this, and this term is finite, so that limit will be 0. When I take the log of this sum, it will go to some 0 because of the log n in the denominator, and this becomes equal to q over twice q minus 1, because it is a minus sign, so it is minus q over 2 over 1 minus q, that is all, and this is the answer for q greater than or equal to 2. What happens at 2? This 2 and this cancels and you have dq equal to 1. So there is continuity in this dq and then it decreases beyond that. So if we sketch this dq, this is what it is going to look like. The generalized dimension for this problem, so here is q and here is dq. It started with the value unity, and this is the origin, here is 1, here is 2 for example, kept till there till this is 1 on this side, it is not to scale, the scale on the vertical axis is 1 there, and then it drops at this point, and asymptotically as q tends to plus infinity it tends to a half. It is easy to see that this is what it will look like. This fashion. So this is the spectrum of generalized dimensions for the logistic map at fully developed chaos. This set of numbers dq is something like the moments of these invariant measures weighted appropriately. So it is an infinite set of numbers, it is actually a function in this case, and gives you information about the distribution itself. Anything for which dq is a function of q and not just a constant is not just a fractal, it means there are many other dimensionalities buried in this system, in this attractor, and this kind of thing is called a multifractal. and dq is sometimes called a multifractal set of exponents or whatever. It is related to other exponents, it is related to other functions which also characterize this distribution. So the whole thing is an effort to actually find out, based on this coarse grained dynamics, what the nature of the attractor is. It is like finding the moments of a distribution, if you like, and then reconstructing the distribution, the probability distribution itself. So that is really what is being done. Let us take another example where you have similar kinds of behavior, and then we will try to draw a general lesson from it. And this was the map in which you had intermittency. So if you recall, we had the square root cusp map which was f of x equal to 1 minus twice the modulus of the square root of the modulus of x, where x was an element of the interval -1 to +1. And the invariant density in this case, because you had a marginally stable fixed point, marginally unstable fixed point at -1, the invariant measure density in this case was a linear function, it was 1 minus x over 2. Okay. So it piled up near the left hand side and tapered off to 0 at x equal to +1, and you have to do exactly the same thing as before. Once again you expect a sort of phase transition, quote unquote, at a point like this at some value of q. Where would that be? Because ultimately what you are trying to do is to find an integral of rho of x to the power q, and when you do that you have this -1 to 1, and when would this diverge? As long as it is finite you could convert the summation into an integration and do the problem very easily. When would it diverge? It is clear if q becomes negative it starts diverging here, less than -1 it diverges, because dx over 1 minus x is logarithmically divergent and any higher power in the denominator and it diverges. So here you expect that at q equal to -1 you have a funny business, and after that, beyond that, it remains a constant essentially, and indeed that is true, and I request you to go through exactly the same steps of before and show, and this is an exercise, show that in this problem dq is equal to 2q over q minus 1. Okay. And what does this look like if I sketch this? Q less than -1, and what does it become at q equal to -1? It becomes 1, so it remains 1 thereafter, q greater than equal to -1. Strictly speaking I should have written this, but then so here is -1 at this point, and beyond this point it remains 1 in this case, and at q equal to -infinity it hits the value 2. Therefore you have 2 here, dq here, and in fact it starts like this, it bends down, comes here, and it goes on. So this is the way dq looks in this case. Okay. So it is immediately clear that if you have some kind of polynomial in rho of x or a rational function in rho of x, then wherever you have the roots of the numerator or the roots of the denominator, as in the other case, you have points of this kind where the slope of dq changes abruptly. In fact it is not hard to show, and I would like you to show this general result. If rho of x, for example, is proportional to, apart from some constant, say x minus a to the power alpha, say, divided by x minus b to the power beta at the two ends, for example, in the interval a to b. Suppose it has singularities at the end points of the range in which the map is defined, then dq has changes of slope at points which depend on alpha and beta on both sides, and it looks like as follows, goes like the following graph. Let me draw it in pictures and then q, you have by the way alpha beta greater than 0, positive integers, so you have this, and that is dq, and this is minus 1 over alpha, this is 1 over beta, and dq starts with a value, at this point there is a phase transition, it remains like this, and then it tapers off to a limiting value which is 1 minus beta, because certainly beta has got to be less than 1, otherwise it is not integrable, and out here it is like this, and this is 1 plus alpha. So d minus infinity tends to 1 plus alpha, d plus infinity tends to 1 minus beta, and in between it hits the value 1, and it looks like that. If you have more products here in between, more zeros and more places where it diverges, then it will show up right there. All those points will in general show discontinuities in the slope of dq. So this gives you some idea of what the generalized dimensions look like. We will come across some other examples in more in higher dimensional fractals, but I urge you to complete these derivations. It is very simple, all you have to do is to use exactly the technique I used for the logistic map. Whenever you can convert things to an integral, you should do so, and then the limit is easy to take, otherwise you must retain the sum and find out what the dominant behavior of the sum is. You can do this very rigorously, but what I did there was essentially right. Okay. Now let us go back a little bit and ask, okay, we have some kind of coarse graining, but can we relate the dynamics of these coarse grained dynamical systems, can we relate this symbolic dynamics to some random process itself? It turns out the answer is in many cases you can. We saw what the idea of a generating partition was. I stated that if you divided up the phase space into cells and kept track of the symbolic dynamics of the trajectory moving between these cells, then if you can reconstruct the actual dynamics by looking at these sequences of letters, then it is a generating partition. Not at all clear if every system has generating partitions, but there are other cases where the partition has other kinds of interesting properties. In other words, the jump of the system between these cells looks exactly like a random process called a Markov chain, and let us see what that is. For that I need to introduce a few concepts in probability, especially in Markov chains, and not clear how much background I should assume here, but let us take our usual attitude and spend a few minutes in a digression on Markov processes or Markov chains. So this is a digression. Markov chains or Markov processes, depending on whether it is a continuous time or in discrete time. Let's do the following. So let me assume that I have a random variable x, and it changes with time, and the time could be discrete or continuous, it does not matter, but let us suppose that this variable generates a time series as I go along. Then how do you specify the probabilities or distributions of this variable? Well, one of them would be to ask what is the probability, and if it is a continuous variable then of course I must talk about a probability density, otherwise I talk about a probability itself, and I will use these two words interchangeably for the purposes of this little digression. I could ask what is the probability that it has got some value x at some time t, and if the time is discrete then it is n. let me for the moment use continuous time and go back to discrete time a little later. So this would give me the probability or the density, probability density, that the function is either that the variable has the value x at a time t or is in a range x to x plus dx at time t. Let me call it P1, it is some function, non-negative function. But this is not enough. I also need to know what is the probability that this variable has, say, a value x2 at time t2 and x1 at time t1. Let us stick to the standard convention and write earlier times to the right and later times to the left. Okay. So you need to know this joint probability as well, 2-time probability. You also need to know the 3-time probability, that it is x3 at time t3, x2 at time t2, x1 at time t1 and so on. Each of these in general different functions. And to specify the random variable completely, I need to know all the joint probabilities for arbitrary number of time arguments. So you need an infinite number of probability distributions, joint probability distributions, to specify the random variable completely, to find all possible correlations in the random variable. However, by definition, Pn of xn tn, xn minus 1 tn minus 1 dot 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 all the way up to x1 t1, by definition this is equal to the probability that you have xn at tn given, and for conditional I put a vertical bar there, given that at time tn minus 1 the variable had this value xn minus 2 at tn minus 2 dot 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 up to the last one, multiplied by the probability that you had all the conditions here, that you had xn minus 1 at tn minus 1, x1 at time t1, and this of course is has n time arguments, and therefore let me call this again n, and let us call this n minus 1. This is a different object than this probability. This is a joint probability, this is a conditional probability. So it simply says that if you have a sequence in time t1 less than t2 less than t3 etc., then the probability that you had x1 at t1 at time t1 right up to xn at time tn is by definition equal to the probability that you had all these earlier events happening at the times indicated multiplied by the conditional probability that if these events, given these events have occurred, at the next time step the value is xn. So this is almost intuitively obvious, this thing here. Well, therefore you can start reducing things, because now you could reduce this to a product of an n minus 1 fold conditional probability that the last one occurs given all the earlier ones occur, and therefore in some sense you can reduce this entire thing to a product of conditional probabilities till you hit this last one. Now that is what you can do in general, that is about all you can do in general. For a Markov process the memory is short, and it is specified by saying first order Markov process means that this conditional probability is independent of all these earlier events and depends only on the immediately preceding event. So it is like a one step memory, that is it. So if I call this the present state, the future, the next step is determined by the present and not by the past history. So for a Markov process, Markov Markov process, this whole thing gets wiped out and you have just this multiplied, of course. So the statement is that the conditional probability, so let me state that again precisely and then we come back and write out our joint probabilities. The statement is Pn of xn Tn given that xn minus 1 Tn minus 1 occurred, x1 T1 is identically equal to some function, and for want of a better notation let me just call it P once again, P of xn Tn xn minus 1 Tn minus 1. There are only 2 time arguments here, so let me just call it P2. It is a function with 2 time arguments, and this is the Markov property. It is called first order Markov. If it depends on the preceding 2 steps then it is second order Markov and so on, but we are going to restrict ourselves to first order Markov processes. Yeah.
How do you define it for continuous time?
This is for continuous time. For continuous time these are probability densities rather than probabilities. Oh, you are asking continuous time as opposed to continuous discrete variable here. These are 2 different events in 2 different time steps, so I do not see any problem there. All we need is this. So at any instant that is true. This is true. His question is, if you have discrete time then I do not have this t here, this is n minus 1th instant and this is the nth instant, then you can understand this. But his question is, suppose time flows continuously, then what are these things, how close to this time can that be? Arbitrarily close, arbitrarily close, still true. That is a good question, we will come back to this and see what it implies. It will imply a certain renewal of the process as we go along. So you can ask, okay, on the time axis if something happened here and something happens here, then we are saying the conditional probability depends on what happened here at this point, but something else could have happened in between. Yes, indeed, that is true. Therefore this quantity is going to obey some kind of chain condition which will propagate you from here to there and then from there to there. We are going to see what that is. But yes, this is a good point. In continuous time this is actually true as long as Tn minus 1 is less than Tn, that is true. But what is the implication of this? It is an enormous implication because it immediately implies that you can take the general n time probability and write it as a factor of conditional probabilities of just 2 time arguments right away, because you can then write this quantity, this n-fold probability to be equal to first the joint probability P2 that you had xn at Tn given xn minus 1 at Tn minus 1, and the rest of the conditional probability, this dependence is gone, multiplied by the n minus 1 time joint probability of this set of events, but that could be written once again as P2 of xn minus 1 Tn minus 1 given xn minus 2 Tn minus 2, and then the n minus 2 time joint probability, but that can again be factored out and so on till you end up with P2 of x2 T2 x1 T1 multiplied by the single time probability of x1 T1. So for a Markov process or a Markov chain, if T is discrete, this factorization is possible. Now what does that mean in practical terms? It means that if you give me the function P2 and the function P1, the job is done. All joint distributions are known in terms of just 2 probability distributions, the 2 time conditional distribution and the 1 time probability itself. So that is the remarkable simplification that occurs for a Markov process. Now we are going to make a further assumption. We are going to assume that the statistical properties of this random variable do not change with time. In other words, that the variable is a stationary random process, that the actual statistics does not change as a function of time, and therefore it implies that you can shift all the time arguments by the same constant and nothing is going to change. What does that imply? It says that this function here is independent of time. Because it is independent of the time argument, you can subtract out the t1 completely. In other words, if you ask for what is the average value of x or the mean square value or any moment of x, this should be independent of time. If I took the nth moment or kth moment of this by definition is dx if it is a continuous variable, p of xt, x to the power n. If it is a continuous process, if the set of values of x is continuous, it is this integral, otherwise it is a summation. But the t dependence appears here, and if this is going to be statistically, all these moments are independent of time, the only way that can happen is if this distribution does not depend on time. Right. Therefore, for a stationary process you have a further simplification. For a stationary random process, p of x comma t, p1 of x comma t equal to p of x, no t dependence, and since no confusion should arise I am going to drop this 1 and just call it p of x. It is a probability if this x takes on a discrete set of values, it is a probability density if x takes on continuous values. It is the stationary distribution. And what happens to p2 of x t x prime, say x naught t naught, say. So the probability, given that you had the value x naught at time t naught, the probability that you have x at time t is independent of t naught. So you can subtract out this t naught from both sides, and therefore this is equal to p2 of x t minus t naught x naught and 0. You could call that the origin of time out there, which for simplicity of notation let me simply write this as again p using an abuse of notation, p of x t minus t naught x naught. In other words, I will not even bother to write down the fact that this is a 0 here, I have shifted the time origin and that is it. I use the same symbol p here, I should not really, I should call this p2 and call that p1, but we know what is happening here. So where is the time argument here? There is no time here at all in the single probability, single time probability, and there is just a single time argument here in this p of t. What therefore happens to this business here, this entire density? Well, it is clear this becomes tn minus 1 xn minus 1, and I can erase this in a little abuse of notation. I write this as because it is really dependent only on this time difference all the way up to here, p of x2 t2 minus t1 x1 and then p of x1. So the matter is simplified enormously. In other words, if you give me two functions, you give me p of x and you give me p of x t x naught, the job is done. There is one time dependent probability or density and there is one time independent probability. You have one more property which you expect, and that is the following. You would expect, you have to establish this, but you would expect that if I took this conditional density or probability which says given that this happened, given this as the initial condition, this is the value at time t, given that this happened at t equal to 0. What happens to this as t tends to infinity? What would you expect? What would you expect would happen to this probability as t tends to infinity? I would expect, if things are reasonable and the system is sufficiently random, I would expect that this probability would become independent of x naught. It should forget the initial condition altogether, and I would expect therefore that you have limit t tends to infinity p of x t x naught to be equal to p of x itself. It should become the stationary distribution independent of the starting point. So that is a consistency condition that I put on the system. If the dynamics has enough sufficient mixing, it turns out this is always going to be the case. So really you have just one function which you have to determine, this, because once I do that I take its limit as t tends to infinity and I know this, and therefore this entire, for arbitrary n joint probabilities, are all determined by a single function of a single time argument, which is this. And what is the initial condition on this? If it is a density, if this x is a continuous variable, then it is immediately clear that in addition to this thing here, you therefore have limit t tends to infinity p of x t x naught equal to p of x naught p of x, and you also have limit t tends to 0 p of x t x naught equal to what? It should have support only at x naught, no, not p of x naught, no, this is the conditional density in x. It is 1 if x equal to x naught in some sense, but if it is a continuous variable and it is normalizable, then what would it be? What would this be? What is the continuous analog of a density which has got measure 1? Delta function, yeah, Dirac delta function. So this should be delta of x minus x naught. So that is the only thing that contributes and everything else is 0. So you have an initial condition, you have an asymptotic limit, and the entire process is determined by this single function, and it is this quantity for which one generally writes equations down, evolution equations or master equations or whatever you call it is written down for this, because after all in any physical problem it is only conditional densities that you can model. You can't model absolute probabilities, you can only model conditional probabilities. Given that a certain event or set of events has happened, you can now talk about the future, but you can't talk about any absolute probability. There is no way of writing equations for these things. So the equation one writes for Markov processes for objects of this kind are called master equations. There are several of them, but depending, some of them are integral equations, some of them are differential equations, and so on and so forth, and there is a very elaborate theory of Markov processes which tells you what these things are, how these things evolve. But now let us go to specifics and let us see how to write this down. So let me work in the context of continuous processes, and after that I will talk about jump processes. We need to do both. Well, there are several ways of doing this, but let me do this in terms of something which I will motivate in sort of in an intuitive sort of way. So I would like to write an equation for p of x comma t, and I drop the x naught for the moment because that is incorporated in an initial condition. saying that P of x comma 0 is going to be some delta of x minus x naught wherever I start. Then I ask if x is continuous, runs over a whole set of values, then I ask what is delta P over delta T equal to on this side. There are two ways in which I can have contributions to the increase of the probability mass at the value x. One of them would be that if the system, well let me motivate this, go back a little bit and write, so I go back, sorry, a little bit, right, P of x comma t x naught at 0 could be written in the following way. Because of this Markov property, you could say that you start at x naught at 0 and you evolve to some value x prime at some time t prime. So on the time axis you have 0 here, you have t prime here, and you have t here. T prime is less than t but greater than 0. You propagate from here to there, and then you propagate from x prime to x in the remaining time. But x prime could have been anything in between, and therefore you integrate over all possibilities. And you expect a condition like this to be satisfied. This is called the chain condition. It essentially renews this process because you are really saying that this process has only one step memory. So it goes from x naught to some intermediate state, any intermediate value x prime, and then from x prime to x in the remaining time. And this is true for all t prime between 0 and t, and there is an integration over the intermediate steps. This has got a long name, it is sometimes called the Chapman-Kolmogorov equation or the chain condition, because it is like a chain which propagate, go from step 1 to step 2, step 2 to the next step 3 and so on. It should really be called the Bachelier-Smoluchowski-Chapman-Kolmogorov equation because several people wrote it down at the same time or around the same time, but we will not go into the history of this. But this equation helps us to write something down for this. I should immediately hasten to add that one should not be under the misconception that this equation is unique to Markov processes. Other processes which are not Markov also obey such a chain condition because it is in some sense a renewal process. All renewal processes would obey similar equations, but Markov processes certainly do. Now what one does is the following: one takes this t minus t prime to be infinitesimal, some delta t for example, very close to t, and then writes instead of this a transition probability per unit time, and that changes this chain equation from this kind of integral equation which is non-linear. It is an integral equation and it is non-linear in this p, to a linear equation for the rate of change of p, and that equation looks like this. So from this it follows, under suitable conditions, delta over delta t p of xt x naught is equal to, on this side, an integral over intermediate states dx prime, the probability that you are at x prime at time t having started at x naught, and then you make a transition from x prime to x per unit time if that transition probability is wx given x prime. In other words, this stands for the transition probability per unit time of making a transition from the value x prime to x per unit time, because we are writing a rate equation here. But you also have a loss term which says you might well have reached x itself at time t, you could jump out of x into any other state, so there is a w of x prime x, and this looks exactly like the rate equations you write down in chemical reactions or any other system which is governed by rate equations. So this is like a gain term. You go from x naught to an intermediate point x prime and then you jump from x prime to x, and this is the rate of jumps. Or you go from x naught to x and you jump out of x to some other value x prime. Okay. How would you write the same thing if you had a Markov chain in discrete time, say? So suppose the values that this variable could take, instead of being a continuous set of values, was a discrete set of values x1, x2, x3, etc., x sub j, and let us suppose this whole thing took place in time. Then how would you write this set of equations? What would you write? What sort of equation would you write here? If it is continuous, if the process is discrete but the time is continuous, then it is very straightforward. You still have a rate equation of this kind here, but you would have a summation here, right? So you would have a summation which is, so let me say W, say x I from the value xj to the value xi, this transition probability per unit time, let me write this as some Wij. So let me write it in this fashion, let us call it Wij by definition. Then what would I write down instead of this? I would write d over dt, and if Pj is the probability that you are at the value xj at time t, then this rate of change is equal to a summation over, let us call it pi, summation from j equal to 1 to whatever the number of set of values you can have, could be infinite, could be finite, times what? What is the integrand? What is the summand inside in that case? What would you write? This, remember, would be, you have to sum over all values, so what would you write here? P j of t W, you have to go from I to j, right, from j to I, so you have a Wij, you will have that, minus on this side Pi of t W ji. With a prime here to show that j is not equal to I. Agree? In an integration it does not matter, because the value x prime equal to x is a set of measures 0 here, but in a sum it matters. So you put a prime here which denotes this thing here, implies j not equal to I in the sum. So that is very much like a rate equation to write down, and once you specify the matrix W, you can write this transition probability matrix as a matrix. Once you write this matrix down, the job is essentially done. Now what kind of solutions do you have for this matrix equation? So let us see if we have a convenient way of writing this thing down. Let us suppose that I call P of t, oh by the way, what is the initial condition on this? What is the initial condition? It is anything at all, depends on what your x naught was. If instead of x naught I start with state k, x sub k, then of course it says that Pi of 0 is equal to delta Ik. If it is at the state k, the probability is 1, otherwise it is 0. So I am starting with some specific value at t equal to 0, and with that initial condition you have to solve this equation. But there is a very convenient way of doing this. Let me write a column vector P1 of t up to Pn of t if you have, for example, a finite number of states, but if you do not, it keeps going forever, we really do not care. So let me write P1 of t, P2 of t, etc. And let me call this column vector the script P of t. And that looks very much like a matrix equation, and what it says is that d over dt of P of t is equal to some matrix W times P of t. And what is this W? What would you say is W? What are the diagonal elements of W, for example? Suppose I is equal to 1, then it says dp1 over dt is a summation over j not equal to 1. So it starts off in this fashion, and it says W12 times P2 plus W13 times P3 and so on. So it is clear that this W has matrix elements which are like W12, W13 all the way in this fashion, and then you have a diagonal element here. What is that diagonal element equal to? So you have, if you put I equal to 1, you have dp1 over dt, there is a term here which is minus p1, but there is a summation over j wji. So this is w21, w31, 41 and so on. Right. So you really have a structure which looks like W is equal to minus W21 plus W31 plus etc. That is this first term. The second term is W21 and the term here is W23, but in the diagonal here you have minus instead of minus W, and what will you have here? 1 2, just as you had 2 1 3 1 etc. you have a 1 2 plus W 3 2 plus and so on. So you have a matrix equation of this kind, which is not very difficult to solve if W is a constant matrix, which is what it is in our stationary case in principle. And then you have a matrix W which determines the transition probabilities, in which the off diagonal elements give you the transition probabilities from one state to another. This is the rate at which from state 2 you jump to state 1, or 3 to 1, and this is 2 to 1, or 1 to 2 and so on, but the diagonal elements are the negatives of the sum of all the rest of the elements of the same the rest of the column. So the sum over each column in this matrix W is 0. So you have a matrix with the property that the elements are all real and the diagonal elements are minus the sum of the off diagonal, the rest of the elements in the same column. And the formal solution to this is of course P of t is e to the Wt times P of 0, and if P of 0 starts at a particular state, then it is a column vector with zeros everywhere except a 1 at that particular state, and e to the Wt acting on that initial column vector gives you the probability vector for all the states. So this is how you would handle discrete valued processes in continuous time. And now if you go to discrete time as well, you have what is called a Markov chain. That too is determined by precisely this matrix of probabilities, something analogous to W. Once again, instead of an exponent e to the Wt, if you have discrete time n, what do you think this will be replaced by? Intuitively, like I have discrete time, what do you think this guy is going to be replaced by? Well, each time to go from time step 0 to time step 1 you are going to apply this matrix W. To go from time step 1 to 2 you are going to apply the matrix W once again. It will be just W power n. Yeah. Just as the discrete version of the Laplace transform is the Z transform, it is just a power, it is exactly the same principle. So you need to know w raised to an arbitrary power, which you incidentally need to know if you want to exponentiate it as well here. But there is an even easier way to handle the matter, and that is to look at what happens to the Laplace transform of this equation. This immediately implies that the Laplace transform of p of t, if I call this p tilde of s, it says s p tilde of s minus p of 0 is equal to w p tilde of s, which implies that p tilde of s equal to s times the unit matrix minus w inverse on p of 0. So it implies that if you have the resolvent of this matrix w, this is called the resolvent of this matrix w as a function of s, you have the Laplace transform, and then you can invert the Laplace transform to find p of t. Okay. This resolvent will exist as long as you do not hit an eigenvalue, as long as s is not one of the eigenvalues of w where the resolvent blows up. You can already see from here this is very similar to what we had for dynamical systems. So the entire behavior of this probability matrix will be governed by the eigenvalues of this transition matrix w, just as it was governed by the eigenvalues of the Jacobian matrix for our dynamical system. So in that sense, these Markov processes, which really have reduced to a set of first order equations, is very similar to a dynamical system. Very similar mathematics is used. Now what I am going to do next is to take a map like the tent map or something like that, do a partition of it and show that this partition can behave like a Markov chain. The discrete time dynamics would behave exactly like a Markov chain, and therefore I can actually tell what happens to n time arbitrary time probabilities, and we will see how that is done next time.